Okay, YouTube, in this video we're going to continue to write quadratic equations from data, but in the first couple of videos that I made, we were actually given specific data about a parabola. That is to say, on the first video we watched one where we knew a point on the graph, we knew the vertex, and we could go write that equation in vertex form. And the last video that we did here, we said, well, we knew the intercepts, okay, and we also knew a point on the graph, so we could go write this thing in intercept form. We are going to look at a unique situation in this video in which we actually have a data set here, and I say, well, let's go ahead and read actually the situation, and I'll talk about how we fit it into this third situation you see up here. But it says, a former NASA employee designs a model airplane that flies in a parabolic path. So we know it flies in this parabolic path. It says the table shows the heights in feet of a plane, and we'll use h to represent that, of a plane t seconds after starting the flight path. So we can see that our times here are increasing, and I'm assuming measuring time in seconds. It says that we're measuring this in seconds here. What we want to do though is write an evaluated function to approximate the height of the model airplane 6.5 seconds later. So you can see that if I were to put 6 on here, we might be able to get a good guess, and 6.5 would be between 6 and 7. What we want to do is really accurately predict how many feet it would be off the ground at 6.5 seconds after it's launched on its flight path. So the thing that is different about this situation is that we actually have a data table. And I'm not really sure that this is necessarily a parabolic path. So one thing I want to do before we actually start this up is I want to look at something that we call a first difference and a second difference, and how you can tell that data is actually modeling something that's quadratic. The interesting thing about quadratic things is we're going to be finding differences between each consecutive set of values here. And what I'm finding here are actually the first differences. So for instance here, if I said 20.4 minus 19.1, all we're doing right now is just to go to show that it is actually quadratic. So we say the first difference here is it went up by 1.3. And then if we look at the next one here, we say, okay, well, 19.9 minus the number before, 20.4. I look at this and I get negative a half, so it actually goes down by a half. And we'll find the next difference here, this first difference between these two things. So we get 17.6 minus this 19.9 before it. And it comes out to be a first difference of, well, a decrease by 2.3. And then last but not least, if we took this 13.5 and subtract off the data value before it, which is 17.6, we say that this is negative 4.1, or the height decreased by 4.1. This would actually be really good if we wanted to extend our table here and make it a really good accurate prediction as to what would happen next. But we see that it stopped kind of increasing, and now it's decreasing by more and more each time. So what we've written right here, we could actually add on another part of our table. We refer to this as the first difference in the table. Now, I don't want to take up a lot of space because I'm going to need this space on the right. But to find the second difference, what you do is we just go ahead and find the differences between these. And again, what I want everybody to know is this. I don't know if this is really quadratic data. I suppose I could go graph it and take a look, but even then sometimes it's difficult to tell. So the second difference is what we want to find. And so what I'm going to say is let's take these first differences and find the differences in them. And if it's quadratic, something really special happens here. So we have negative a half. Take away this 1.3, we get negative 1.8. So the second difference here, negative 1.8. If we take this negative 2.3, so we have 2.3, it is negative. We'll take away this negative 0.5 before, so 0.5, which was negative. I get negative 1.8. And would you believe it, if I do this again, if I take negative 4.1 minus this negative 2.3, it's this, it's negative 1.8. So it's not so much this value that I care about here as much as is if this is a constant thing or nearly constant, its second difference, then we say that its first difference is actually changing by the same amount every time, which models what we call acceleration. So if that's the case, then we do model acceleration things using parabolas. So that being said, finally, all this being said, I wanted to prove that this was a quadratic data set in the first place. What I want to do now is write a quadratic model, and then we're going to use that model to make this prediction 6.5 seconds out. So this third situation here says, well, what you need are 3 data points. And the interesting thing is, it doesn't even matter which data points we choose to use here. I'm actually going to use probably just the first 3, but we have some x and y pairs. We know that when x is 1 second, or when t is 1 second, we get a height or h value or a y value, output value of 19.1. So this will be our x1, y1. we'll have an x2, y2, and an x3, y3. You'll notice that I say here, write and solve a system of 3 equations in 3 variables. And it says write the equations in standard form. So we know that we have these different forms of a parabola or a quadratic equation. We're going to use standard form on this one. And so when we write our first equation here, basically what I want to point out is that we have our x value is 1 and our y value is 19.1 if and only if our x value is 1. So what this is going to look like is this. Our first equation would say, well, our y value is 19.1. I'll put this in a different color here. 19.1, but it's only true if our x value is 1. So what we get is this system here that says a times, well, 1 squared plus b times, well, 1 plus c. So here's our first equation, and really what I'm going to point out here is that if you simplify this, we get 19.1 is equal to a times 1 squared, which is a, plus b times 1, which is plus b, plus c. This is our first equation. Now, setting up our second equation, we say, well, what's our y value? And I'm going to go ahead and fill all this stuff in here, just in standard form. And we're going to plug in our x and y respectively. So we say when x equals 2, when we are 2 seconds later, we knew that this plane was at a height of 20.4 feet just by our measurements. So simplifying this, we would get 20.4 on the left for our y value here, and we'd say 2 squared, well that's 4. So we get 4a, and then 2 times b is 2b, and we have this plus c here. And I hope you notice this, when we plug in this last data value here, we say, okay, well now I've got my y value, when my x value is, whatever, and I say plug this in. The c value is always plus c, so it's going to make solving the system actually kind of easier. And so what we'll see here, no pun intended, is that we have a height of 19.9 feet, or at least the plane obtained a height of 19.9 feet when we were 3 seconds into its flight. So we'd say our final equation after simplifying it is 19.9, and we get that this is 9a plus 3 b's plus a c. So this is our 3 by 3 system here. I'd say that the hardest part was setting it up. Now we can just go solve it. So what my plan is this. We'll go ahead and add equation 1 to negative 1 times equation 2. I'm going to do that, equation 2. So if I rewrite this now, we have 19.1. I'm just going to go ahead and rewrite my first equation, a plus b plus c. And we'll add that to negative the second equation here, which is negative 20.4. And this would be negative 4a. Negative 2b, and negative c. So when we scribble this out this time, what we find out is that our c's definitely cancel, and we end up with this. Now I'm going to need my calculator here. Actually, it would have been smarter to add negative equation 1 to equation 2. We would be dealing with positives, but you know what? It's a mental exercise. So negative 20.4 plus this 19.1. We get a new constant of negative 1.3. We get negative 1.3 is equal to negative 3a's and then minus a b. I'm going to put a box around this. So this time, since I've learned my lesson, what I'm going to do is this. I'm going to add negative 1 times equation 1, since that has smaller values. And I'm going to add that to equation 3, and I'm going to cancel out my c's. So we get negative equation 1 would be negative 19.1, negative a minus b minus c. And then our third equation here is 19.9 positive, and we have 9 total a's, 3 b's, and a c. So again, our c's cancel out in this instance, and what we get is a difference here of 0.8, it's positive, and I get 8 a's plus 2 b's. I'm going to put a box around this. The reason why, and I'm going to have to borrow some space here, you're going to have to forgive me, is because now we have 2 equations in 2 variables. And so what I notice here is this. If I were to stack these, negative 1.3 is equal to negative 3a plus, minus a b. And I say that this equation here is 0.8. And we have that's equal to 8 a's plus 2 b's. What I notice is that I could get my b's to cancel very easily if I actually double this first equation and then add it to the second equation. So what we find out is this. We have double that first equation. I'm just going to stick it right below this here. We say negative 2.6, negative 6 a's, and negative 2 b's. When I add these up, I get my 2 b's to cancel. We end up with 2 a's left over, and 2a is actually equal to the difference between negative 2.6 and a positive 0.8. So we say 2.6, which is negative, plus 0.8. I get negative 1.8. And solving for a now, I can just divide both sides by 2. What I've just determined is that a is equal to negative 0.9. I'm going to put a box around that. So we have our a. Plugging this back in now to either of our two variable equations, I'm more inclined to use this one here because it has smaller values. Then I'm going to put this up over here. We say negative 1.3. We have negative 3 times a, which is negative 0.9. And then we'd say that's minus b. What we figure out is a negative times a negative here, of course, is a positive. So we have negative 1.3. This will be a positive 2.7. This is minus b. And when I subtract 2.7 from both sides now, we're going to get this negative 1.3 on the left, negative, minus 2.7. So I end up with this negative 4. So in other words, if negative 4 is equal to negative b, then we have that positive 4 is equal to b. So now, check this out. Now we know b. Now we know a. The only thing left to do is go plug this back in one of the original equations, and I'd say that the easiest one to deal with here is this first one. So I'm going to borrow more real estate over here. We say 19.1 was equal to a, which is negative 0.9, plus b, which we just found out is 4, plus c, which is the only thing I don't know. So we have 19.1 is certainly equal to now negative 0.9 and a positive 4. I'm just going to do some mental math here. We get 3.1 plus c, and if I subtract 3.1 from both sides, what we just determined is this. 19 minus 3 is 16, and 0.1 minus 0.1 is 0. We get 16.0, so box it. So not only could we say that our ordered triple would be negative 0.9, comma 4, comma 16 with respect to our system, what we could say is then this equation, because it had to be in standard form, this ax squared plus bx plus c form, we could say must be equal to negative 0.9 x squared plus 4x plus 16. So I understand that this is a lot of work that you have to go through, but really it's kind of a simple thing. Once you get your system set up, we just need to go solve the system, and I'm guessing you have more room than I do. So because of time, what I would like for anybody that's watching this to do, wouldn't be bad for you to go through here, and maybe you don't need to go through and find all your first and second differences. I will just go ahead and tell you that this is a quadratic data set. But pick out 3 of these data values here, and go ahead and set up a system of 3 equations and 3 variables, and work to figure out what a, b, and c are, because once we know what a, b, and c are, we can go ahead and just plug them in for a, b, and c here, and just like we've done in the past, leave x and y general, and you'll have the equation of this vertex, this parabola in standard form.